Oh, God. So going around is a 7-wire strand. We confirmed that there are indeed 7 wires. Maybe you missed the middle one.
I missed the middle.
Maybe you missed the middle one. This is going on. This is another view of that one going on up at Big Sky that they sent us. So there's another one going to be here in Bozeman. It's the podium slab. God. Okay, I'm ready. Are you guys ready?
Yeah, we're just talking about how counting is hard, but math is easy.
Good point. Okay, so then we're gonna do a tour of a post-tension floor design. So they're doing one here in town as well, and then you worked on this. Is this right? This is up at the
Big Sky one?
The
Yeah,
Big Sky one.
I think I did the submittal reviews for those PT slabs.
Yeah, see, Tony thinks
Good.
maybe
They look correct.
They worked on that. Yeah, and so this is kind of neat. I mean, we'll learn about this, but you can see it's like going up and down as it goes along to go positive, negative moments, depending on if it's going. So there's a beam going through here, and so then the floor slab's going over the top of that, and so it's going positive to negative moments. Then there's also pretty interesting how they can sweep it to the side, which always freaks me out a little bit. So like you're pulling, but then actually you're pulling and then it sweeps around the corner like this, and then there's limits to how far you can sweep horizontally as you go across it as well. So that's literally happening right now. He's up at the job site, and actually up at the job site, oh, what's going on? I was making fun of him because he was supposed to, oh. This is what's happening on the job site right now in a different location. They've cast the concrete, and then that is the big post-tensioning jack that's applying the load to the tendon that's going into the concrete right there. It looks like this is like a midway, because you can only pull a certain distance. You can't pull like super long distances, so there's a limit on how you can do that. So right in the middle of slabs, sometimes they have a little breakout section where they can pull, and then later on they're going to pull that side as well. They'll pull both of those. So it's happening.
Continuous strand through it then still?
No. Nope, there's a break, and then they'll jack and then put the anchors on this side, and then on the other side they'll do the same thing. Actually, maybe there isn't on that side, but sometimes you'll see it where they have it on both sides, and then they'll come back afterwards and cast concrete in the little joint in between. So we'll see that when we go out to the job site. There's one here in Bozeman that we're gonna that we'll tour at some point. I mean, if you want to see this is Strava. This is Axel Strava. He's running the rut next weekend, and then I was making fun of him because this is his running so far. He did 9 miles, 4 miles, 3 miles, right? The 4, 0, 3, 0, 3, 0. And I was like, dude, you're ready. You're ready. You're ready. And then some of you may remember. Do you guys remember Madison Lechte? She was the. See, this you might remember her because she was the engineering mechanics helper, right? She is running. This is her last week. 93 miles last week. Right? And so she's doing the rut. Those of you familiar with the rut, she's doing all 3 days of the rut. So she's doing the first day, which is incredible. Then the second day is like 50 miles, and the third day is like, whatever. It's a massive amount too. So she's doing all 3 days. The trifecta is what they call it. And I was just like, yeah, you're just right up there with Madison. You guys are just right along the same. You guys are just right there with each other. Although he's young, and I'm sure he'll do just fine in the 1 day of rut. That's what's nice to be. You could get off the couch and just do stuff like that. If I got off the couch and did that, I'd probably be paralyzed. I think somehow I would die. Right? I need another duty. Yeah. So then we were in the middle of talking about doing this design, right? We did actually talk about stuff last week beyond just identifying animals. So we're looking at direct solve is one way you could do it. So you go into this thing, and we know something about the demand, right? We know the moments that we're trying to design for. We know the span. We know the support conditions. We know material strength. And then, in fact, a lot of times in most of our design, in our problems we're going to do in class, we're even going to know the dimensions, like what is the cross section. So in your homework for this week, we give you, Sean's not here.
He has to get a combine, he said.
He has to do what?
He has to get a combine this morning.
Okay.
He said that he would make it in class.
Okay. And then They would give us a known dimensions, right? I'll tell you what the shape of the section is that you're designing. So you're going to know the area of the concrete, the moment of inertia of the concrete, the depth to and from, the extreme to the extreme compression and tension fiber. And we'll also probably, in a lot of the designs, I think the design I gave you here, I'm even going to tell you what FP is, what the total pre-stressing force is. And really the thing that we're going to be designing for is EP, right? We're going to kind of assume, obviously if you start from scratch, you have to design all of it. But right in the homework though, I'm going to give you everything except for EP. And then you have to just decide where that EP is going to be. And if it's okay to be in those locations. He's just moving, right? He's just moving from one eyebrow to another eyebrow. Oh my God, it's so bad. I don't know. I think he's going all the way down, so we have to wait for him to go all the way down. I know, right? I don't understand how they're allowed to be here at all, right? Like, what the fuck? Okay. Oh my God, dude.
I'll just stand at the windows.
Just stare at him. Just stop the beeping, dude. You don't need it in reverse right now. Oh God. Okay. All right. Now back to this. Right. So there's a couple different methods that we're going to do. We're going to do the direct solve. Your homework's going to do this direct solve, and then we're also going to do tendon profiles. So your homework has you doing tendon profiles. Has anybody done the homework yet? Kira, come on, Kira. You're slacking, dude. You're slacking. So anybody look at the homework.
I opened it.
Oh yeah, Neil. Yeah. You go. Nope. It's long, isn't it? It's a long one, right? But the idea is once you get your program working, all we're going to do is you're just going to be plugging in different like EP values and stuff like that. That's what a lot of it's walking you through, and different tension limits and stuff. But once you get it working first, it'll be fun. So then there's the equivalent load method. That's what they do in PT floor design. We're not going to do that, but we'll at least talk about it. And we've mentioned it several times what it is. The PCI design manual, we will look at that, right? It's good for preliminary design. It's basically load tables. We're not going to do Mangel diagrams. We're not going to do a computer program, but that's what you would do in the real world, right? And then we're not going to do C-line method either. So this direct solve method, right? This is we're just go to this equation, and what you're doing with this is you're plotting the stresses along the length of the beam, right? And you do that. You have to do this for each load stage, right? And you have to do it for each load stage, right? And on that plot, right, you have the stresses at the top and the stresses at the bottom, and you put the limits for the compression and the limits for the tension. And as long as your stresses are within the limits, you're good to go, right? And so, like, again, it's going to look something like this. I think this is actually what your homework solution will look like, right? Here's initial load stage and then the total load stage. And you plot the stresses at the top, and here's the stresses at the bottom, and you look to see as long as you're within them. If for some reason, if this line right here crossed over the top of this, it would say that we would have tension at the top under initial conditions. That would be a failure. If for some reason this one dipped below, and it's a long ways away, but if it dipped below this red one right here, it would say that you would have compression at the bottom. You'd fail in compression at the bottom in the middle. Right? And then same thing, it can happen at the ends as well, right? And I think in some case, one of your cases today, or for your homework, you do a straight tendon profile. And in the straight tendon profile, I think it violates the tension at the top near the ends. And so you'll see that it doesn't have to be controlled in the middle. The reason I have the sustained and the total loads as being different, because remember, there's a different compression limit for sustained loads. For sustained loads, they have a lower compression limit, 0.45 F prime C instead of 0.6 F prime C. So one of the big differences is where that line is at, where the compression limit is, right? This compression limit is higher than this compression because it's the 0.45 for 0.6. And the reason sustained has a lower compression limit is because you're trying to avoid creep issues, right? Sustained loads cause creep, right? And that's why we have this intermediate load state. This is really under service conditions, right? But it's when we're looking at just the sustained loads, right? And then that problem statement has the live load broken into sustained and transient, like what's going to be there all. Then this is the total one, right? And you can see that the closest thing, you're getting really close to a tension failure for this particular load case. Right? And this is just for one of the tendon profiles that I gave you, right? Because there are other ones in there that do fail, that do cross these lines you have to go on. This is the one that actually works in your homework. Okay. Cool. Let me see. That's the direct solve, right? The tendon envelopes is the other way to do it, right? And this kind of flips it a little bit. Think of it slightly different, okay? So it's use the same equation, right? But in this case, what we do is, let's kind of call out things that we know here. We kind of flip it around where this is known, right? We know this. From the code, right? The code specifies what that's going to be. So you enter into this equation knowing what F2 is, right? We also know what FP is, right? That's a known going into it, but that's also going to depend on the stage. Come on. On load stage, right? Do we have the initial condition, or do we have pre-stress losses, or do we not have pre-stress losses? So that FP is going to be known. M external, right? That's also going to change along the length and the load stage. Length and depends on load stage. And then the one thing that you don't know at this point, or we're going to assume we don't know, is this EP. And so what we're going to do is we're going to solve for this. Right, so we're going to assume that is an unknown in there, right? So you just kind of flip it around, right? Instead of just solving for F2 and comparing it to limits, you put in F2, right, or F1, depending if you're looking at the top or bottom. You put that in, you put in the right FPs that you're using, you put in the right external load that you're using, and you solve for EP. You could just algebraically kind of flip this equation around and come up with an equation for EP as a function of those things, right? And that's going to change along the length. And what that ends up being is it ends up being a limit, okay, on where you can put your tendon, right? And so I say solve for EP, solve for EP, and this is a limit of eccentricity. Okay, and I'll explain it more and show you what it looks like in a second. So you get an EP limit for each load stage and controlling limit state. You plot these EPs and that's what we call the envelope. Because you'll see that you'll end up with certain lines you have to stay below and certain lines you have to stay above, and then you have this little region that works, right, that you're not going to limit things. You're going to have 4 limit states per load stage. What those are compression, top and bottom, and tension, top and bottom. right? Technically, you're going to have that many, right? That's a lot, right? But we can apply, right? We could simplify it significantly and apply logic down to 2 limit states per load stage. Right, for simply supported. And we did this once before, or at least talked about this. Right? And what I mean by that, like being able to simplify it down, I mean this table right way up here, just this one, right? Right? When we talked about which load stages control, what I have boxed are the ones that control. See, technically each one of those, all of those actually have to be true, but when it's simply supported, then the only ones we really care about are the ones we have boxed right here, right? And so you could simplify it down to those 2 per load stage. Right? That's going to be, like under initial load stages, that's going to be tension at the top and compression at the bottom. And then under service load conditions, it's going to be tension at the bottom and compression up at the top is what you care about. Okay, so let's see what that looks like when you do it. Okay. Oh, let's use this one, a fancier version of it, yeah. All right, so this is, I kind of drew it slightly different. So on here are those basically 4 limits, 2 for the initial conditions and 2 for the, and then technically there would be that one sustained load floating around, but I don't have it in here. So you might have to think of that one a little bit on what to do with that sustained load. But what I have on here, right, is that's exactly what I did. I put in, look at the initial service condition, right? Tension at the top under initial conditions. What I did is I went to this equation up here, right, for that, and I put in FPI for my FPs. I put in my self weight, because that's the only thing that's there for this load right here. And I put in the tension limit that came out of ACI for there. And the only unknown was EP. I solved for that EP. It's going to change as a function of X. It's going to change as a function of X because M external changes as a function of X, right? And so then because M external changes as a function of X, then that EP will change, right? Later on, that's right. So it's going to be the external moment's going to do that, and you're going to solve for the EP. So that's what I did, and then that's what it gave me this blue line right here. You can't really see it. This blue line right there, right? And then I did the same thing for under initial conditions. I found the compression limit state, right? And again, be careful of your signs, the negatives and positives. If you're doing compression limit state, when you go into F2, you put in a negative value, or F1, you put in a negative value for your allowed stress limit, and then work out the details, and then there it goes. So that's this blue right here is under initial conditions. This red one right here is under initial conditions. Then I went on to the next load stage, and I said, all right, under service conditions, I'm going to have tension at the bottom and compression up at the top. I plugged them into those equations, and then I got EPs. It's function of X because the M external changes, right? And then there they are right there. They're almost right on top of each other. The blue and the red are right there next to each other, right? And so then in order for the beam to be okay, I have to be higher than this value and lower than this value. And that's why I have the stuff painted or colored as yellow right there. That's where I'm allowed to put my tendon. As long as my tendon fits within those limits, I'm good to go, right? And there's certain lines that you have to stay below and certain lines that you have to stay above, depending on what limit state you're looking at, right? If I'm worried about my tension down at the bottom, tension at the top under initial conditions, right? That should be a lower limit, right? Because if I dip down below that, right? If I move my tendon below that, it's going to pop it up more, and then I'm going to get tension at the top and compression down at the bottom, right? I'm going to get tension up at the top and compression at the bottom, right? Same thing with the initial load stage right here, right? The initial compression, same thing. That's going to be a lower limit. If I go below that, I'm going to get too much compression down at the bottom. On the other side of things, under the service conditions, I can't go above these lines, right? If I go above those lines, then I'm going to get tension at the bottom and compression at the top. And so you can see this is, I've mentioned this several times, it's this this ongoing battle between your service conditions and your initial conditions, right? And so your initial conditions are saying you got to stay up there, right? You got to go above. You got to go above lines, and your service conditions are saying you got to stay down below these things, right? What happens if these lines cross these lines? You can't work. It's impossible, right? Your tendon, there's no place for your tendon to go, right? And so I think in your homework, one of those things happens, right? You're going to get one where your stay below limits cross below your stay above limits, right? And I did it. I think I'm pretty clever. As I put in dashed lines for the lines you have to stay below and solid lines for the lines you have to stay above, right? And so because I'm clever, I could do that, right? And then I came back and I filled in with the yellow. So anywhere that this yellow is, you could put your EP, right? You could put your tendon, right? And then what's interesting is you'll see in your homework, there's going to be some cases, like I said, that don't work, right? Where I think I put in a straight tendon profile that goes through here, and then it hits these things. And so what this is my tendon envelope, and then these are the stresses down below. And so if I find a problem with my tendon envelope, I'll see them show up on my stresses as well, right? Because they're all tied together. They're all the same thing. Right? And so that's where I'm allowed to put a tendon. And if for some reason, this crosses below this and it says you can't do it, you got to change something. And usually what you got to change is you got to change your material strength, right? If you change your concrete strength, that would help some, right? If you changed you'd have to go back and redesign it. You could change your section size, right? You do something where you can get it to work. But that's that, right? So that's how you would design with these tendon envelopes. Kind of a fun little exercise to do. I think it's a fun exercise to do. That's basically exactly what your homework is. It's setting this thing up and basically making the plots that you see right here, except for you're going to do it with a bunch of different like EP values, right? Where I make it fail and don't fail and stuff like that as it goes along. The first times I started teaching this class, every single homework assignment, all the beams always failed. And then my students were like, do you think like maybe once in a while we could get one that like works? I was like, deal. And so then now you're going to get some that work, right? Here's one that works, right? But you're also going to get some that don't work, right? Any questions about that? You excited? Kira, I'm disappointed you're not done with it yet.
I'm sorry. I'll get straight to it.
Get straight to it, yeah. And then I always have to mention this, stick with the sign convention. Be careful, right? If you don't put this in as a negative value when you're putting in the compression limits, things won't work out. You'll get some weird answers, right? And then your S's for the top and bottom, again, have to have their signs in them as well, right? You'll have to come up with equations for M external as a function of X, as a parabola and stuff. So you'll figure it out. Okay. So then the next thing, let's talk about the PCI design manual, right? That's another way that you can kind of do preliminary design. This is Precast Institute, right? There is also PTI, which is the Post Tension Institute, right? It's interesting because there's standard sections, right? Just like an AISC has standard steel sections and stuff like that. There are standard pre-stressed sections, right? These things are made at factories, and so because they're made at factories, they have to have some standardization but amongst all the different factories out there. And this PCI design manual is where it's at. Usually concrete, we get to pick whatever size we want, and you get to frame it up. PT design, you do that, but in precast design, you have to select from standard shapes. They only have standard sizes that they cast and stuff anyway. So they have like a design manual to help with this, okay? I'd say that this gets used in preliminary design. I even talked to some real engineers out there, and they say that, yeah, they'll use the PCI design manual, but just for the preliminary. And we'll look at the assumptions that it makes. Lots of assumptions made that may not be valid. And so you got to go back and check it afterwards and make sure it's okay. And one of your later homeworks, we do that. We pick one of these and confirm that it actually can carry the load that it says it can. So these are precast, pre-tensioned, made in factories. Actually, even on this homework, you're going to use this a little bit because I think I have you grab one of the sections out of this, right? I mean, I keep looking at Kira, but she hasn't started it yet. Has anybody besides Neil looked at it? Gavin, do I use
I just opened it.
I think I used a section out of here. I was like, go grab a,
Said something about ACI trying to find the standards there.
double T or something like that I have you pick, or a T section, or an inverted T. It might have been an inverted T. That was just an exercise of you guys opening it up and taking a look at it, okay? So then the way these things work, right, is, I mean, they're load tables, right? They have a safe superimposed service load. So you can figure out how much service load you need, and then you come in here, and it has for different spans and feet, so you should know your span, and you should know what the service load is. And these gives you that. What is that?
Sorry, guys.
What happened?
What's going on?
Oh, it's going, okay. That was a tough game, Neil. The hell, man. I really feel like we just fucked ourselves a lot with all the fumbles and stuff, right? Like, if it wasn't for that, I think we looked great, you know?
Yeah, that was a big one too.
What was that?
The too many men penalty.
Yeah.
When it's 4th and 1 for them.
Yeah.
Fun.
It's all right, though. Right? I mean, they're a good team. Right? We'll see them again, possibly. Okay. Yeah. I will admit I did not watch it because this is I'm not joking. How I watch football is I wait to see who won, and then if my team won, then I go back and watch it. If my team lost, I don't go watch it.
Did you watch that game last night? Bills.
I did watch that game. I did watch that game, and it's unfortunate because I started watching it because I wanted the Ravens to win. I started watching it because they were up by 2 touchdowns, and I was like, great, because I have anxiety issues. I was like, great, we're up by 2 touchdowns. I don't have to worry about this. And then lo and behold, the Ravens then lose, and I was like, fuck. But also, I like Josh Allen though, right? You think so? He's pretty good.
He was last year.
Yeah, he's good. He's from Wyoming, right? And then what's the relationship with Vegan?
He coached me a while.
He coached up at Wyoming, so I had to be like, okay, fine. But I just really like Derrick Henry.
Derrick Henry lost that.
I know he fucking lost. It's his fault. But he also had 175 yards. Sorry, everyone else that don't watch football. Eagles won. That's the. How did you think we looked?
Looked good on defense.
Yeah, the offense is.
They were 1 for 13 on 3rd down.
Were they really?
We were 3 for 15, so not good.
Yeah. No. How's the elbow? Done?
No more fast ones.
Yeah. All right. So then here it is, right? Here's the allowable loads that you can put on these things, right? And then over here they tell you stuff about, we're not at least initially we're not gonna use their numbers, but this is where this is where they're gonna put their tendons at, right? Because they're gonna kind of change where their tendon is because it's gonna have some eccentricities. You got to be careful when you're using these tables because their variables that they use are different than the variables that we use, and so you just got to be a little careful about going back and forth between those things, right? But then there they are, right? So it'll tell you what the allowable load that you can put on this, okay? But what goes into this table takes into consideration initial conditions, service conditions, and ultimate loads, right? The VMN and greater than or equal to, or VMN greater than or equal to MU, right? That's built into this as well, okay? So they're in there. Where you figure out like all the assumptions that it makes for the design, right? I mean, it'll tell you all sorts of stuff. It tells you, it tells you what the strand pattern is, the number of strands they're used. It tells you the diameter of the strands in 16ths. It tells you this, is it straight or depressed? The depressed would be the case where you would have just a harp section with one depressed point in the middle, but versus straight being have the tendon go straight across. And then how many depression points? In this case, it has one depression point, or sometimes it'll do the 2 depression points like that as they go across, right? And so it'll tell you all about that, and that's all built into these tables. And it could be a really nice way of doing a preliminary design, okay? And then what goes into these load tables, right, is it goes through the sections right after the load table. So this is in PCI Design Manual under Chapter 3, right after all of the load tables, or probably right before the load tables. It tells you in paragraph form what it took into consideration when making these things. This is, when we get to ultimate loads, it tells you the load factors that it uses. It tells you what it used for its tension limits for the double T's versus the other stuff. It tells you what fee factors it used and how it went about doing that for the shear design, right? It tells you there's my compression limits and tension limits up there. Right? It tells you how it estimated its cambers. Those things are built into it as well, right? And so when it comes time, like I said, we're going to have another example where we actually go through and we double check that their beams actually work in design. And you're going to have to dig into these tables deeper. Right now, we're not going to dig into the tables, just besides just looking up some material properties, right? Because each of these sections, it tells you, what they are. Right? And so I think that's what you do in this week's is you just look up its moment of inertia. And this is what I'm talking about, what it uses. I think we're using C in a place that it's using Y. Right? So you just got to be careful of these, and they're doing SB and ST instead of S1 and S2. So just be careful of those things. Cool. Okay. So then that's one of the design methods. The other one is this thing called a Mangel diagram. This is something that Stanton spent lots and lots of time on when I was in graduate school. And in this article about the sign convention, he spends a lot of time. I didn't like him. I hated him. I still don't understand him. We're not going to do it. I don't know what it has to do with, right? So just know that is a Mangel diagram, a Magnell diagram. And at least say what it's used for. Because just in case you run across it in the future, it optimizes pre-stress forces and locations. Right, because this is the EP is part of it, right? In these design equations, EP is part of it. But the other thing that's floating around is FP, right? FP comes from how many tendons. That's what your last week's homework is. How many tendons do you need? Stress to what value? That's a design variable as well. Back to that case before where one line crossed the other line, one solution would be to increase your pre-stressing force or decrease your pre-stressing force, depending on, it'll move both of those lines, right? So what do we use for the actual pre-stressing force? Well, it's a design consideration. So there's two things there. So there's like infinite number of solutions, right? And this Magnell diagrams was all about like optimizing that. And I never understood him then. I don't want to understand him now. So you're a gift to you. I'm not going to make you do Magnell diagrams. All right. There's also computer programs. We'll look at those. They have pre-stress computer programs and they have post-tension floor design programs, depending on what it is that you're designing. They have their specialty for doing those things. Did you get into design at all, Tony, or just?
I did very briefly. It mostly just checks.
Did you use it? What program did you use a program?
RAM concept.
Yeah, Rand concept. Yeah, right. So we're gonna have Kyle Boyd. He's a practicing engineer, and he did a bunch of this. He's gonna teach our class for a couple weeks because I don't know what I'm doing in terms of post-tension floor design. He's done it a lot, so he's gonna teach our class, and he'll talk to you and show you the programs and how they work, just like at a pretty high level. But they're pretty cool. They work pretty nice. Yeah. What's that?
I think I should teach the class instead.
Oh, have you done post-tension floor design?
No. I'm just named Kyle.
Oh, that guy. Yeah, that Kyle's like. Right, and then the other thing here is pre-engineered, right? Which is kind of that PCI design manual stuff. But I hate this. I hate doing this. But like, because this is like I'm teaching you how to do pre-stress design. But say like in the real world, right? And you're like, oh, I got a bridge that I'm going to do, and it has to span this much, and I have this many girders that I need. What you do is you order it up from the pre-stress plant, and their engineer designs it. That's really what happens, right? You don't do it. They do it. The person that works in the shop, they pre-engineer. They design it themselves, right? They're like, oh, this is what they do for a living, is all pre-stress design. They just go through and they tell you this, right? Make it this big, make it like this, put the strands like this, and you're good to go. So if you don't work in a pre-stressing plant, right, then you don't need to know any of this shit because it just comes in pre-engineered. That being said, you might work in a pre-stressing plant, right? Or, I will say this, I did talk to MDT folks about this once, and they do that. They order them up, and then they get pre-engineered, and when they come in, they double check that they're okay. right? Because you're not just gonna trust, like you're not gonna, but you do trust them on trusses, right? Like a pre-engineered truss, like you don't go back and check the trusses, do you? Right, worker people. Yeah.
I checked the loading they use.
Yeah, that's about it. But you just assume that maybe it's because it's a truss and it's easier, right? Like, I mean, trusses are pretty easy.
Or they just kind of plug numbers in there.
Yeah, they plug it into a program and go, right? But with these, like at least with MDT, they double check the pre-engineered pre-stressing beams when they come in, right? And so what they do, and that which is different than design, right? To do an analysis, what they probably do is open up their computer program and put in all the design assumptions and then the section and then make sure that all the stresses are okay, and they probably get a big okay at the end and stuff like that. But but just keep that in mind. That's floating around. Post-tension floor design, completely different, right? That is not pre-engineered. That's something that you do. Sometimes it gets subcontracted out, right? Like if you're doing it and then like, well, shit, nobody in our office has ever did a post-tension floor design, and you're like, here, with this other group, do this for us, please. And so it sounds like maybe that's what happened up at Big Sky. Like, how did you guys end up doing it over at?
The Big Sky Hotel is actually a Denver Big Sky project, so that's
Oh, that's bullshit.
just, like, completely out of
That's
Denver
bullshit.
office.
That's bullshit, Tony. That's ours. That's what's Montana.
I don't know why it's Denver specific. I think it's probably because they have a lot of experience with like,
That is probably it. Right. Instead of us just making it up as we're up here, right?
yeah.
We've done a little bit more these days. It's happening. It's catching on more. It has some major benefits in floor design. We mentioned using PT floor design. Right, and we mentioned this. We'll talk more to allow for use in FEA programs. We mentioned that before, right? FEA programs they're not set up to deal with internal moments, right? They don't know what to do with them. And so then you turn them in to equivalent external loads, right? And then you put those on the structure. And then the load balancing thing has to do with you try to cancel out the extra. So you want the internal moments to cancel out the external moments. That's what it means by balancing. Is you want the internal to cancel out the external, want them to balance each other out so that the effects go away. Okay? But it's a big thing. You'll hear Kyle, not this Kyle, the smart Kyle. He'll talk about. Actually, when you hear him talk, he doesn't sound very smart, but he's actually incredibly smart. He sounds less smart than I sound less smart. I'm missing all this. Neil's throwing shade at you. Is that good?
Pretty much, yeah.
Good, he needs it. All right. So that's some interesting notes. I mean, that's it. That what we're going to do with this PT floor design. You got some homework. So we'll talk about what our next step is. This is all elastic analysis. We're under elastic analysis, right? And that's allowable stresses. Are our stresses within the allowable limits? That's what this is all about. Then after that, then we have to make sure people aren't going to die, right? And that's the ultimate loads. That's where we're going to go. We'll get into that on Wednesday, is calculating the ultimate moment and making sure that the phi mn is greater than mu, and then we'll do phi vn is greater than vu, right? Then we'll calculate deflections and talk about how you do that, and we'll calculate pre-stress losses, how you estimate pre-stress losses, and then we're kind of done with the pre-stressing stuff, and then we'll jump over in post-tension floor design. That's when Kyle's gonna either come in or do it remotely, okay? And kind of teach us how to do the post-tension floor design. And then we'll do an exam, and then we're gonna switch over to bridges, and it's just all, no homeworks or anything. We're just gonna, maybe I'll throw in homework. That was too excited. You were too excited about no homework, but. Animal matching homework. Okay, some interesting notes. So this is a little finishing up of this elastic analysis. Okay, so sometimes they do this strategic debonding of pre-stressed tendons, right? This is pre-stressed, right? This is pre-tension, pre-stress stuff. That's where this would work, okay? And what happens with this, right? If I look at this beam right here, if we look at what the external moments would look like on this thing, right? They would be a kind of parabolic, right? So these are the external. This is M external. Right? I have external moments. And then in this case, I just have a straight tendon, right? Those are really easy to do. Straight tendons are easy to do. And then in pre-stress plans prefer to do that than have those depression points, right? And so we have a straight tendon going across like that. And then near the ends here, right? And so that you can run into problem. You could, well, even with under service loads, say we had service loads, you had a total load on this thing. Near the ends, even under service loads, there's little external moment on there, right? But we have this big internal moment that's coming from these pre-stress tendons. And so what can happen is you can get cracks at the top in this region right here, right? Near the ends. Even under service conditions, you can get cracks at the top. And it's because this is not, like when it's depressed, right? Then we're trying to, you're having it start at the CGC on the ends. And so there's no internal moment in the middle. In the ends. But if you don't do that and do a straight tendon profile across, then you're going to have these big internal moments. And if those big internal moments get big enough compared to there's no external moment there, you can get cracking near the ends, okay? And in order to fix that, what they do sometimes is they just grease up the end and they debond the pre-stressing on the end, right? And this only works, right? It only works for pre-tension stuff, right? Because post-tensioning, right, you're applying the loads afterwards and stuff like that. But in pre-tension, as they do, so they stretch their steel out, right? And then they come in and they grease the tendons in this region right here. They grease them up, right? Or put a sleeve on them or something so they won't bond to the concrete. Then you cast the concrete around it, and then you cast the concrete around it, and then you release the stresses or release the tendons, the stresses in the tendons, and they transfer over to the concrete. Well, they don't transfer in here because it's not bonded, right? It won't start the transferring until you're in a certain distance, right? To however far it was that you debonded it. And then that'll prevent cracking up at the top. Just a little side note, kind of a clever way to handle it. And that way they can avoid having these issues, but then also not have to depress it, right? Or not have to harp it or drape it or whatever, right? That's kind of an interesting topic. We'll write that down for you. Can get cracking, cracking from pre-stressing at top near ends. No moment out there to counter internal moments from pre-stressing force. Just when you come back and look at this later on, you'll know what it is, what we're talking about there. Have a neat little workaround there. All right. Another thing that pops up is this statically indeterminate beams, right? And there's some interesting things that happen with this, right? Clearly, you wouldn't do this. I just want to point that out. You wouldn't have a beam that looks like this, right? Because you've got, obviously, if you load this sucker up, right, it's going to go, right? It's going to go, positive moment, negative moment, positive moment. So you wouldn't put a tendon down at the bottom. This is just going to demonstrate what happens with this, okay? When you put an eccentric tendon down like this, right, we've got this extra point in the middle, right? This, we'll just talk conceptually at this point. We'll write this stuff down next time. We've got 3 minutes. So, right, this right here, a tendon, so ignore this for now, right? Just think of this thing, or just the beam itself, right? That eccentric tendon, right, what's it gonna do to this beam? Just the pre-stressing alone. Pop up, right? Because you're pushing, right, this pre-tensioning is gonna push like this, it's gonna wanna pop up, right? But then when you start considering this, I got that there that says you can't pop up, right? So the pre-stressing says you're gonna pop up, but then this right here says you can't pop up because I'm holding you down. I've got a support here. You can't pop up, and so that's gonna cause this internal moment. This weird thing that wasn't there originally, right? This is just ignoring all the loads that's applied to it. Just the pre-stressing alone is gonna have. I'm gonna have this internal moment that's going to be constant along the length. It's going to be a negative moment that's popping this thing up. But then I'm also going to have a big pre-stressing force, or I'm going to have a big reaction force holding it down because it wants to pop up. And so that thing is called, what they call it, the secondary moment, or they sometimes call it the hydrostatic moment. That it's not like there's not due to external forces. It's all from this internal pre-stressing, and it comes about because of this weird thing that's happening, because you're trying to hold the thing down, and it won't let it pop up. And like I said, we're not going to do this, right? We're not going to let it do that. But what we are going to have, right, are those tendons that are going like this, like all along, like in the post-tension floor design. They're all over the place. Are we going to be perfect with that and have exact? No. There's going to be some cases where, it drifts a little bit, and there's going to be these hydrostatic moments that are all over the place. It'll end up real quickly getting out of hand. You can't actually calculate that by hand. It's going to be finite elements that have to keep track of that. But when we get into this a little bit later with Kyle, and we're doing floor design, he's going to talk about those quite a bit, because that's something you have to take into consideration in your design, right? It's just an interesting topic that pops up, right? And then we'll do ultimate moment. So we'll finish these notes. We'll finish this and kind of formalize that next time, and then we'll dive into calculating the ultimate capacity next. Break.